Okay, so in the previous example, example 3, we found that the radius of convergence was r equal 1. Remember, we got that absolute value of x minus 2 has to be less than 1. So this tells us how far our x value is away from 2, and it needs to be less than 1, and we'll get a convergent series. Okay, so we know that our series will converge on the open interval from 1 to 3. All right, if we go left 1, we ended up at 1. If we go right 1, we ended up at 3. So for x values greater than 1 and less than 3, we're good. We have a convergent series. What we don't know yet is what happens at x equals 1 and what happens at x equals 3. All right, so to get the correct interval of convergence, we've already found the radius of convergence, but to get the correct interval of convergence, we need to find out what happens at the endpoints. All right, we may get a convergence series at x equals 1 and not at 3. We may get a convergence series at 3 but not at 1, or we may get a convergence series at both or neither. All right, so when we test the endpoints, we're actually going to plug this x equals 1 in, and we get this series. All right, so for x equals 1, our series x minus 2 to the n becomes 1 minus 2 to the n, which is negative 1 to the n. All right, this is an alternating series, but it diverges. All right, and it diverges by the nth term test. The limit of these terms does not approach 0. All right, they just alternate back and forth from 3 to negative 3, 3 to negative 3, 3 to negative 3. If we plug in x equals 3, we get this series, 3 times 1 to the n. This series also diverges by the nth term test. Right? So the interval of convergence here is an open interval from 1 to 3. All right? So if we kind of think back, when we're working on these problems, when we're working on a radius of convergence, we're trying to find a radius of convergence, we use the ratio test, and then we may get some condition upon x, like we did here. The absolute value of x minus 2 has to be less than 1. This gives us our radius of convergence. We can take that further and ask for the interval of convergence. In that case, we plug in the endpoints. In this case, it was 1 and 3. And then the series that we result in, or that we get as a result, we have to test for the convergence of that series. So this is when all of our other tests are going to come in. In this case, in both cases, we use the nth term test to show divergence. But we have to keep in mind all those Chapter 9 tests that we used, they might come into play here when we're working on these ones. Right? Our next example, find the interval of convergence for x to the n over n from n equals 1 to infinity. Right? So we use the ratio test to find the radius of convergence. Right? We show the limit as n approaches infinity of a sub n plus 1 over a sub n, absolute value of. We show that limit. We're left with an x and an n over n plus 1. The limit as n approaches infinity of n over n plus 1 is 1. So we're just left with the absolute value of x. All right. In order to have a convergent series, that absolute value of x needs to be less than 1. So the radius of convergence is r equals 1. So that's the radius of convergence. Right? So one thing that we didn't notice here, hopefully you noticed, we're really talking about a power series centered at 0 here. Right? So if the radius of convergence is 0 and we're centered at, the radius of convergence is 1 and we're centered at x equals 0, then our endpoints are negative 1 and 1. So we have to plug in each of those endpoints. If we take this series and plug in x equals negative 1, we get an alternating series that converges. If we plug in x equals 1 to our series, we get 1 to the n over n. That's just 1 over n. That's a divergent p-series. Right? So in this case, the interval of convergence is closed at -1, and open at 1. Right? So you can see that in this example 5, we got the same radius of convergence. We still got a radius of convergence of 1, but this time one of our endpoints turned out to be a converging series. So here we're including -1 and excluding 1, whereas in the previous example we excluded both of the endpoints on our interval of convergence. All right, just one more thing to note. When we're talking about radius of convergence, if we get a power series and we take the derivative of that power series or the integral of that power series, the radius of convergence is always going to be the same as the original power series that we started with. All right, but the interval of convergence may change. So if we take the derivative of power series, we know the radius of convergence stays the same, but we still need to retest the endpoints because the interval of convergence itself may be different than the original power series that we started with.